How do bridges stay standing against wind, earthquakes, and thousands of cars every day? Today, we'll uncover the hidden engineering that keeps the world's most impressive bridges standing strong. Bridges aren't just steel and concrete, they're lifelines. They connect people, cities, and economies. But every bridge must battle the forces of nature, gravity, wind, water, and sometimes even earthquakes. At the heart of bridge engineering are two forces, tension and compression. Tension stretches materials, while compression squeezes them. Every bridge balances these forces to stay standing. In civil engineering, a load is any force or weight applied to a structure, such as a bridge, building, or beam, that it must support or resist. Loads cause stresses, deformations, or motion, so understanding them is essential for designing safe and stable structures. When cars drive across, their weight, called the live load, spreads through the structure. The bridge transfers this load safely into the ground through piers and foundations. Engineers also account for dead load, the bridge's own weight, and dynamic loads like wind or traffic vibrations. Let's define some of these loads. Dead load, the permanent, static weight of the structure itself, such as the bridge deck, beams, cables, etc. Live load, temporary or moving forces like cars, people, or wind gusts. Dynamic load, loads that change quickly or cause vibrations, like moving vehicles or machinery. Thermal load, expansion or contraction caused by temperature changes. Seismic load, forces generated by earthquakes that shake the foundation and structure. Wind load, pressure exerted by wind on the structure's surfaces. Hydraulic load, pressure or force from water flow or waves acting on a bridge or dam. Soil or foundation load, the reaction of the ground supporting the structure. The simplest type is the beam bridge, a horizontal beam resting on supports. The longer the span, the greater the bending moment at its center. Engineers use equations like m equals F times d to calculate the bending stress, ensuring the material can resist it. Arch bridges redirect compression along a curved path into their foundations. This makes them incredibly strong for short to medium spans. Ancient Romans used stone. Modern engineers use reinforced concrete or steel for greater flexibility and strength. In an arch, each block, called a voussoir, presses on its neighbor. The central stone, the keystone, locks them together. The shape channels weight sideways into the ground through abutments. That's why an arch bridge stands even without mortar. Suspension bridges carry the roadway from massive cables that hang between tall towers. The cables are under tension, while the towers experience compression. The deck hangs from vertical suspenders that transfer load to the main cables. Designing a suspension bridge requires accounting for aerodynamic stability. Wind can make bridges twist or oscillate, as seen in the Tacoma Narrows Bridge collapse in 1940.
Dawn of a fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile-an-hour gale, the center span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now. There's an automobile caught on the heaving roadway. The 11,000-ton center span twists and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick. Back out of the danger zone, all stricken spectators are driven to safety as the bridge gyrates like a nightmare high above the river, twisting, turning, curling. The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure? but he saved himself by seconds. No structure of steel and concrete can stand such a strain. Steel girders buckle and giant cables snap like puny threads. There it goes! Engineers are divided as to the cause of the disaster. Some claim it was the use of solid girders. Others differ. But whatever the reason, Tacoma will rebuild. This time a bridge that will not provide a super thrill in the news.
Engineers now use wind tunnels and computer simulations to predict and prevent resonance. The Golden Gate Bridge spans 1.7 miles and stands 746 feet tall. Its main cables are over 3 feet thick, made from 27,572 individual wires, enough to circle the Earth 3 times. Engineers allowed slight flexibility so it could breathe with the wind. Cable-stayed bridges are a newer innovation. Instead of hanging from a single cable, the deck is directly supported by cables that fan out from towers. Each cable acts as both tension element and stabilizer, making these bridges lighter and more efficient. Engineers analyze cable-stayed bridges with finite element modeling, a computer method that simulates stress and deflection under load. This ensures uniform tension across cables and stability during temperature changes or uneven loading. The Millau Viaduct in France is the tallest bridge in the world. Its highest pylon rises 343 meters, taller than the Eiffel Tower. It handles wind speeds of up to 130 kilometers per hour with aerodynamic deck design and tuned dampers that absorb vibrations. The Millau Viaduct was assembled from both ends of the valley using incremental launching. Each section of the steel deck slid forward on Teflon pads until the halves met in the middle, a feat of millimeter precision. Modern bridges rely on advanced materials, high-performance steel, fiber-reinforced polymers, and pre-stressed concrete. Pre-stressing adds internal compression, letting concrete handle greater tension loads without cracking. Before opening, every bridge is tested with simulated loads, sometimes fleets of trucks or hydraulic systems, to measure deflection. In operation, sensors track vibration, temperature, and strain to predict wear before failure. Wind can create lift and oscillation. Engineers use aerodynamic decks, slotted surfaces, and tuned mass dampers to minimize motion. The Akashi Kaikyo Bridge in Japan, for instance, adjusts to strong typhoon winds without damage. What we see above water is only half the story. Towers rest on massive foundations sunk deep into bedrock or anchored with piles. In soft soil, engineers use caissons, watertight chambers that allow workers to excavate underwater safely. Bridges in seismic zones include base isolators, flexible bearings, and ductile joints that let the structure move without collapsing. During the 1995 Kobe earthquake, these innovations saved key bridges from total failure. Tomorrow's bridges will integrate AI and real-time monitoring. Fiber optic sensors will detect microscopic cracks, while drones perform visual inspections. Some prototypes even feature self-healing concrete using bacteria that repair cracks automatically. Bridge design now also focuses on sustainability, reducing carbon footprints, using recycled materials, and protecting ecosystems. The goal: bridges that stand not only for centuries, but responsibly within their environment. From ancient stone arches to carbon fiber spans, bridges represent human creativity and resilience. Next time you cross a bridge, remember, it's not just a shortcut, it's a masterpiece of engineering. Thanks for watching. If you enjoyed learning about the world's most impressive bridges, don't forget to like, subscribe, and share. And stay tuned for more STEM adventures here on Skill Render.